if Maximilian could somehow make his way, then I can definitely solve 918 maximum sum circular subarray. Okay. So you're given a circular integer array nums of length n. Return the maximum possible sum of a non-empty subarray of nums. A circular array means the end of the array connects to the beginning of the array, right? So the next element after the last element is the first element, right? So it's circular in that way. A subarray may only include each element of a fixed buffer nums at most once. All right, so I can include each number once as long as it's in a row, right? I have to choose consecutive elements. I can't do like a subsequence thing. I can't just pick random elements, right? I have to pick elements in a row consecutively. But there's also this added feature where I can wrap around the end, right? So we want to find the maximum subarray, but it's also possible that that maximum subarray is the wraparound subarray because there's a circular aspect to the system. So in this example, right, the maximum subarray is just 3 alone, right? Because if you tried to do 3 and -2, you're going to get 1. If you tried any other subarray, right, it's going to give you something smaller than just using 3 alone. This example is using that circular feature, right? Because the maximum subarray is 5, 5. Well, how did you get 5, 5? You can't do 5, 3 or 3, 5 or 5, -3, 5. But if you do 5 and then circle back to the beginning and use this other 5, you get the subarray 5, 5. So there's this, There's this circular feature that allows you to get an output of 10 using the wraparound aspect. And then this is just showing that, nothing in here is good, right? Everything in here sucks, right? Including any element will give you something negative, but the idea is you have to choose at least some subarray. You can't return an empty subarray and say that the output is 0. So this is just trying to articulate that point. Okay. So our constraints, 10 to the 4, so n squared probably won't be acceptable. So we're probably going to try to think about something that's n log n or better, okay? Now, we know that there's an n time O of n time algorithm, a one-pass algorithm to solve maximum sum subarray without the circular constraint. So let's first think about that problem and solve that, and then use that maybe as kind of a foundation to address this additional feature, which is the circular aspect of this problem, right? Because there's a really common problem, which is just finding the maximum sum subarray. And, that's a good place to start. And usually that's one of those like fundamental problems, like maximum sum subarray, two sum, right? There's a few, balance of, invert a linked list or whatever, right? There's a few problems that are like fundamental foundational problems, and maximum sum subarray is one. This is kind of a added, like built on top of that problem. So it would be common in an interview where maybe you had multiple questions that you'd be given the maximum sum subarray problem, and then this was given as an additional problem if you were able to solve that initial problem. But the point really is of this long rant is that you should probably know just from memory how to solve maximum sum subarray. Like that code should be indented within your brain. And I'll go through quickly the logic of that code, but I'm not going to spend too much time focusing on that because that's something that you should probably either already know, or if you don't know, there's going to be a multitude of resources that you can utilize to learn that problem solution if what I explained right now isn't sufficient. All right, so with that said, let's go ahead and get right into it. So to find a maximum sum of a subarray, not considering the circular aspect, what you're going to do is think about what you get from each element. So it's kind of a greedy approach. I mean, I guess you could say it's dynamic programming, but the idea is for this problem here, right? What we can do is think of this as like a graph where every time you look at an additional element, you add it to your solution. Okay. Now, I've never really thought through how maximum sum subarray works. So if my explanation here is a little clunky, Just understand that I, who've solved, hundreds and hundreds of Leetcode problems, just memorize that solution and know to use it as in application. So that's really the important point. Sometimes it just comes down to memorization, but hopefully this will give you a little bit of intuition about how this problem works. So if you have 1 as a subarray alone, you'd say, okay, that would give me 1 point using 1. So let's list each of these elements in this plot. So the vertical axis, right, this y-axis, that'll give you information about how many points you get, or what the sizes of the subarray you're using. 1, 2, 3, and -2. What if you use -2? Well, if you use -2 with 1, you're going to get -1, right? So you'll get down to -1. I didn't plot that here. But I guess something you should think about here is, well, if I have -1, right? If I'm using 1 to -2, I'm going to get -1, which is never going to give me something good, right? Like if I'm using a subarray and it's providing me with some negative information, right, it's not going to improve my score, right? If I want to use 1 and -2 together, it's going to give me a total of -1 extra points. But I'm trying to maximize my score. So if it gives me -2 points, if it gives me -1 points in total, I might as well not use it, right? Because I want to use elements in my subarray that I'm returning if it increases my score, right? If it increases the total number of points that I get. But if I use -2 right now with 1, it's only going to make my score -1, right? So if I'm 3, right? If I'm 3 and I'm asking, hey, -2, should I use you in my subarray to maximize my score? And -2 says, well, the best thing I can provide you with is -1. Well, if the best thing you can provide me with is negative, then I shouldn't include you. So to articulate that, we'll just say, okay, since this returns negative, we'll floor it at 0. Okay, so when 3 asks -2, hey, what's the best thing you can provide me with? It'll say, okay, the best score I can provide you with is 0. And that corresponds to providing you with nothing. Okay, 1, 2, 3. So that's basically what's happening here. This element asks the previous element, what's the best subarray you can provide me with, and give me the corresponding value. 1 is its own subarray, so when -2 asks 1, it says, hey, what's the best thing you can provide me with? It says 1, so it's like, okay, I'll attach myself to that, and that means that the best thing I can provide is 0, which is nothing, because the best thing I can provide, including me, is -1. Okay, so then 3 says, okay, I asked -2 because that's the only person I can ask to get a subarray. Like, hey, I want to include you. What can you provide me with? And -2 says, nothing. I can't provide you with anything, so don't use me. And 3 says, okay, didn't you provide me with 0? So I'll get a sum of 3. Now -2 says, okay, 3, what's the best you can provide me with? 3 says, well, the best I can provide you with is a subarray with just myself of 3 and size 3. And -2 says, okay, cool. So I'll include you. So then when it's 3 and -2, you get 1. Right? And then let's just say, for the sake of argument, I know it's not given in this problem, but if there was a 5 here, or a 1, let's say there's a 4 here. Okay, just so that we have an additional point to think about. So when 4 now goes, 4 says, hey, -2, what can you provide me with? -2 says, yeah, look, I know I'm negative. I'm -2, right? I know I'm negative, but there's a subarray ending at me that can provide you with 1 additional point. And 4 says, all right, sucks that you're -2, but you can provide me with a subarray of size 1, or not of size 1, of sum 1, so I might as well use it. 1, 2, 3, 4, 5. And that will attach here. So even though -2 is negative, right, it has a subarray that is 3 and -2, which has a total size that's positive of 1, so it's going to improve the score. So when 4 asks -2, -2 can provide it with a subarray of size 1, and 4 will add that to its score. So now it can provide whoever comes after with a subarray of size 5, right, which is 3, -2, and 4 together. So that's the basic idea of this solution. And then what you would return, let's remove this 4, because that was just an additional data point to make this example a little more involved. but the solution would just be the maximum, right? Whatever the maximum score is or sum is that you can get using this approach. So you would basically just say like the DP, right? We'll call it the dynamic programming approach, I guess, for an element. We'll call it an index, right? Because each of these things are an index. So the maximum subarray ending at this index equals what? It equals itself, so the value of this index, plus the maximum subarray ending at the previous index, right? And somewhere you'll have to do what? So I guess what you should say then to kind of make sure this constraint works is, well, if my value plus what the previous things can provide me, the previous max can provide me, is less than 0, what will I do? I'll just say, well, I don't want to provide a negative value. So if my value plus whatever the best thing before me can provide me with is negative, I don't want to provide anything. So I'll just say I provide nothing, which is providing 0. Okay, so all we need to do is keep track of this DP value as we go through the system, right? So we don't actually need to create a whole DP. We can just create a variable that keeps track of this, right? So we need a variable that keeps track of this information, and then we need another variable that keeps track of the total max of DP as it goes through, right? That way we can use constant space. So we'll quickly do that. So hopefully this didn't take too much time, but you basically have your current max sum, right? And your max sum. So we'll call it max sum and max cur sum. Okay. So the max sum will set it equal to float negative infinity, just as an initial value so that it gets updated to something. And the max current sum is this. So you look at each num and nums, right? And you say, okay, the max sum, which is like that DP value, and our max cur sum is what? So, So the max current sum would be this DP value here. So the max cur sum equals the max of the value plus the current max cur sum from the previous iteration in 0. Okay. So max cur sum, so something else will go here. So that's the max of the max cur sum plus the current value, which is just num, because we're looking at each value in the system. Because this will give you the max cur sum from the previous element. And if that is something negative, we'll just update it with 0. And then our max sum will just be the max of whatever we think is the max sum and whatever this system can provide us with. Okay, so this is essentially the fundamental problem that solves max subarray sum, right? And then you would just return the max sum. But this won't work for everything. It might work for the example problem because I think it's the first example. But what it's not going to work for, right, is 5, -3, and 5, right? Because this needs to wrap around. This won't be able to wrap around, right? This will say 7, right? Because it'll do, okay, the max is 5 minus 3 is 2, so then 5 can use 2 and get 7. But the actual maximum is what? It's 10. Why? Because there's this wraparound idea. Okay, so that's where this problem gets a little tricky. So we kind of addressed the first way that a maximum sum can occur, which is you start from the left and you go all the way to the right. But there's also a case where what? Right, we have the case where we have some array, you know, A, B, C, D, E, F, G, H. And somewhere in here, you know, there's a max sum, and we select that max sum from the system like this, right? But there's also another way that we can get a max sum, right? A, B, C, D, E, F, G, H, where we grab, you know, sum from this side Right, we grab some from over here, and then we grab some from over here. I'm just generically using letters and generically choosing, but the idea here is what? That you can choose some from the left and some from the right, and you add those together. Okay, so you either take the maximum subarray from this system, or you take like two smaller subarrays from the left and from the right, right? Because in this problem with 5, with 5, -3, and 5, right? Using the first approach, you would use everything, and that would give you 7, which is what we saw when we looked at the example. But there's also using this second approach where you like carve from the edges, right? So you say, okay, I'll use from the left, I'll just use this, and from the right, I'll just use this. And notice when you do that, you get 10. Okay, so what we really want is we want to grab, you know, for some elements, we want to grab the sum of these, right? We want the maximum. We want to grid a prefix here, so we'll call this a prefix, right? And we also want a suffix here. So the idea is that we want to like maximize some combination of prefix and suffix as long as there's some elements in between them, and we'll just call that some subarray, right? Because there can't be overlap, right? Like you can't use one element more than twice. So you can't like grab all these elements and then grab these elements, right? So there has to be some space in between the two elements called sub, right? I have to grab some prefix and some suffix, and there has to be something in between, right? Because if there's not something in between, it's either I grab the whole array, which is the first case, or there can't be overlap. So since there can't be overlap, there has to be some sub in between them, okay? So I'm trying to grab something that maximizes what? I'm trying to maximize the prefix, and I'm trying to maximize the suffix. Now notice that the whole sum of the whole array is going to equal prefix plus sub plus suffix. Right? That's the sum of the whole array. So that means that the maximum of the whole array, if you just work this around, right? So if you say, okay, well, then that means the sum of the array minus sub equals prefix plus suffix. So that means you can replace this with sum minus sub. So that's the same thing as saying the max of the sum of the array minus sub. Right? So how do you maximize this? Well, sub is going to make this thing smaller, right? So I'm basically saying if you want to find the maximum prefix and suffix, that's just this. Well, it just turns out that prefix plus sub plus suffix equals the sum of the array, right? Because I'm just taking some prefix of the elements and adding them together, and I'm taking some suffix of the elements and adding them together. But if I add up the prefix, the sub elements that I'm not using, and the suffix, I get the sum of the array. And then just doing algebra, right? If I subtract sub on both sides, I get prefix plus suffix, which is this. So then I can just substitute that. Now, you maximize this by doing what? Well, the larger sum is, the smaller this is going to be. Right? So the smaller sum is, the larger this is going to be. So that's the same thing as saying the maximum of the sum of the array minus the minimum of the sub of the array. Right? Because you can kind of walk through, because there are like logical like distribution rules about maxes and mins, but just think about it like this, right? If I want to maximize this statement, I want to minimize sub, because I'm minusing sub. So to maximize the thing, I want to minus as little as possible. So to maximize this whole thing, I want to minus as little as possible. Maximizing the sum of the array, that statement doesn't really make sense because the sum of the array is just the sum of the array. It's a constant. So the maximum of a constant is a constant rate. The max of 7 is just 7. I don't have anything to compare it to. So the max of the sum of the array is just the sum of the array. So that's the same thing as this. So this second case of finding the maximum prefix and the maximum suffix and adding them together is the same thing as summing the array and minusing the minimum of the subarray. So it really comes down to finding the minimum subarray in the system, right? Which makes sense, right? Because like, imagine that this was the minimum subarray in the system. So if I thought of this problem in a similar note, right? We said that this was the max and the max. Well, what if we just took the whole sum and we subtracted out the minimum? Well, you'll notice that if we take the whole sum and we subtract out the minimum, right? Doesn't that look familiar? Well, it's the same thing as this, right? So as long as we subtract out the minimum from the whole sum, we'll get two parts, right? Because we'll get the part at the left of the minimum and the part at the right of the minimum. And that is the max of the prefix plus the suffix. So this is the kind of intuitive way of thinking about it. And this is just literally using the math and trying to walk through what it leads you to. Okay. So instead what we can do is we can also keep track of the min sum and the min cur sum. And then we'll also have to keep information about the total sum. So the min sum will set a float infinity as its initial value, 0, and total sum is 0. And then we'll just do the opposite problem here. So min sum is this, min cur sum, and we'll do total sum too, I guess. This would just be the min, right? I don't even need to think about it because it's the same problem, right? Just the negation of that same problem. So I do the min of this, the min of min cur sum plus num and 0. And then I'm just adding in the total sum. So total sum plus the current number I'm looking at. So then at the end, well, I have the two cases. I have the first case where I just use the initial approach of finding max sum. And I have the second case where I'm taking the total sum and subtracting out the minimum sum because that will give me this prefix suffix idea. So I kind of do both things here. I do this first case first. I consider the first case and the second case, and I'll just take the maximum of those two at the end. So the maximum of our max sum and our total sum minus min sum. And yeah, there you go. So we'll go ahead and run that. Okay, so the problem is that with this problem, the minimum sum in this system would be the sum of the whole system. So when you subtract them together, you get 0, but you have to include some element, right? The problem in here is, right, when you have -3, -2, -3, the total is this. But then also the min sum is this. So then you're going to end up deleting everything and you're just going to get 0. And you have to choose something. So if your max sum is negative, that means that you can never pick a positive number. You can never pick something that's good. So you're just going to have to return that. You can't have an empty solution. So this just ensures that you... This just ensures that you have a non-empty solution. All right, and there you go. So this is a one-pass solution, which is pretty cool. So let's say that n equals length of nums. Okay. And then we'll do time. Well, we just have to look at each number. This is a constant operation, and this is a constant operation. So that's big O of n operations. And then for space... Well, we create this variable to keep track of max sum, this variable max cur sum, min sum. So we have these 5 variables that we update, and at the end we just return one of those. So there's just 5 variables regardless of how large n is. So that's constant space. All right, guys, this was actually a really difficult problem. And it took me a long time to see this idea of max minus min. It's a very kind of mathematical sort of intuition that you have to have. And if you don't see it, you're just not going to see it, and you'll probably just struggle. So I don't know. Maybe sometimes think about what information is provided and what information is negated. You know, what can you gather from information? I don't know. This is a very difficult medium. Definitely one of the harder ones. But there you go. Have a good one.